what was the main idea of principal component regression? So the principal component regression first extract the principal component and then define regression problem with the principal component and then find the parameters for the principal component regression problem. So the definition of principal component was, for instance, the first principal component G1 was argmax Z having unit length, of course belong to n-dimensional Lie space that maximize G transpose X matrix. So what is the meaning that maximize G transpose X with the unit length? Which basically find the unit direction, the direction among n-dimensional Euclidean space that has the largest variance of your matrix X signal. The largest variance means when you project all your columns to one single dimensional space, how can you keep the variance of your columns of X as much as possible? That is the definition of first principal component. The first principal component is the direction among n-dimensional Euclidean space that keep the largest variance of your original input matrix X. In that sense, your matrix X is contain P columns, P data point in the n-dimensional Euclidean space, P points in n-dimensional Euclidean space, and G is the direction that has the largest variance among the P input points. So input point means the input vectors comes from X matrix. Okay, so the X1, X2, X3 up to XP, each columns are input point, and we want to find the direction that has the largest variance. Okay, so why we have to extract the largest variance direction? Because in general we have this belief: high variability keep the high information. Okay, so dimension reduction is compression technique. So from the original P data point, we will just use m number of vector points in n-dimensional Euclidean space. And we want to m very representative data point in n-dimensional space so that m data point can explain the input and output relationship very accurately with very small residual sum of square and with very small test error as well. To do that, we have to very carefully choose m-dimensional or m vectors that keep the most information of your input X. Okay, so if this is true, principal component regression is the best, because principal component is the most variable directions, right? So principal component regression is the best because the m vectors or m references extracted from the principal component algorithm or singular value decomposition algorithm is the best in terms of high variability. We cannot design any other algorithm that can be better than PCR, principal component regression algorithm. But in some cases, this is not true. Although some direction has high variability in terms of input X, but the direction can be totally independent to your output Y. This is possible. Okay, so in some data point, high variability does not imply high information. So when you learn PCR, you will observe very bad RSS and very bad test error as well. So to resolve this issue, some researchers invent partial least squares. Okay, partial least squares basically use the output Y as well to find M vector or M reference point to define the new regression problem. Okay. Right. So then what is partial least square? Partial least square first define Z1 in this way. X transpose Y. So this is the first partial least square reference vector. So this is again n-dimensional, right? Because X is n by P, X transpose is P by N, Y is N by 1. So when you multiply X transpose Y, then you end with the n-dimensional vector. Okay, what is G2? G2 is X2 transpose Y. So the equation almost same, but you have to define X2 matrix using Z1 and the original input matrix X. How to define X2? X2 is equal to X minus G1 transpose over G1 transpose G1 times X matrix. So what is the meaning of this? What is the meaning of this? This is projection matrix. Projection matrix projecting onto the one-dimensional space defined with the direction of G1 vector. Okay, so basically this is equal to identity matrix minus this projection matrix times your input matrix X. Then what is the I minus projection matrix? Identity minus projection matrix is another projection matrix which is orthogonal to the original projection matrix. So which means X2 is the matrix which is orthogonal to Z1. Okay, so from the original input, we removed all components aligned with Z1 so that we make a orthogonal new matrix X2. And from the new defined X2 matrix, we can define the second component, Z2. So this is the second G2. Third G3 is X3 transpose Y. Again, we want to make X3 so that it is orthogonal to G2. How can we define X3 matrix? X3 is equal to X2 minus G2 transpose G2 X2. Then X3 is orthogonal to G2. And one other remark is, because X2 is orthogonal to G1, this is naturally orthogonal to G1 as well. So basically, G3 is orthogonal to G1 and orthogonal to G2. So you can define up to Gm in this way. Okay. So here the important point is, when you construct G1, G2, G3 up to Gm, you always use the output vector y. You always use the output label y vector. So which can guarantee your all directions G1 through Gm will contain some huge information with respect to the output y. G1 through Gm has high enough information to predict output y. So you can expect better performance in that sense. Then what is the problem of PLS? So let's compare PCR, principal component regression, and PLS, the partial least square technique. So PCR, which is independent to y. So we never look the output y when you construct the reference vector G1 through Gm. On the other hand, PLS always look at the values of y when you construct G1 through Gm. Okay? So this is dependent. Right. So independent to y, which can guarantee this can solve the overfitting issue. This definitely reduce the number of parameters orthogonal to the output y. And then we can use less parameters, less information of your input, and then you can escape from the overfitting issue, especially when the number of data point is less than the input dimension. But PLS, since it looks at the y values all the time, although when it used the very small m value, very small reference vector for training, it used much less parameter, but still it has very high correlation to output y, and it looks the output y when it train, which means it can have a high chance of overfitting even if it uses less parameters, because it look at the output y all the time. This is kind of cheating. So when you learn the cross-validation, one very important part was we have to never look at the output y value when we train the parameters. Otherwise, it is cheating. So your training error will very underestimate the error, right? So same thing. When you train PLS, maybe the RSS value for your training data point is super nice. You have very tiny training error using very few parameters using PLS technique. But don't be happy with that observation. PLS always look at the output Y, so the training error totally underestimate the error. Your test error, what we really want to minimize, can be worse than PCR. So PCR can be very bad when your input and output has no correlation with some directions. But PLS can have overfitting chance all the time. Okay, so I strongly recommend to use cross-validation to decide either use PCR or PLS. Because it is very hard to say which one is better than the other one. Sometimes PCR outperforms PLS, but sometimes PLS outperforms PCR.